All right, so day 2 of related rates. You have a general kind of understanding of how they work. Hopefully we've done the balloon activity in class at the whiteboard, and you're understanding that things are changing, but they're changing, and how one thing changes affects the other thing. So we're going to be doing that in a more mathematical way today. So here's our first example. This is a real related rates problem, and for every real related rates problem, I recommend making a box. And I recommend using dreads. Okay? Now, we kind of talked about that on the other video, so I'm assuming if you watched the Related Rates Day 1, you know what dreads stands for. I won't write it out. We have a spherical balloon. So here's the good news. Anytime you have a spherical balloon, I'm going to give you the formulas. So the first thing that you need is you need an equation, and that's going to be the volume of a sphere is 4/3 pi r cubed. Okay, that's going to be the volume of a balloon, spherical balloon. So don't worry about memorizing that. Know the Pythagorean Theorem. Know the area of a circle. Know the circumference of a circle. But as far as the volume of a cone, the volume of a sphere, the volume of a cylinder even, surface areas, you don't need to know those. They'll be given to you on the exam. So we have a rate of 4.25 cubic feet. This is the first thing I want to look at. This is air being pumped in. This is a rate of 4.5 cubic feet per minute. So what do you think that represents if we have volume and we have radius here in this equation, right? Do you think that represents the volume changing? It's a rate. It's the way the volume's changing. Or is that how the radius is changing? That'd be how the volume is changing, right? So the way the volume is changing is always going to be dV dt. That's the rate at which the volume changes is 4.5. And it's positive because the volume is increasing. It's going up. So we have a positive change in volume every time. And now they say, find the rate of change of the radius. The rate of change of the radius. So I guess that's our question mark. dr over dt, the rate of change of the radius is our question mark. When? Now this is very important. It's when the radius is 1 foot, right? The radius is not always going to be 1 foot. Because imagine this balloon is being pumped up, right? And you have this video here, or this little picture. The radius of that balloon is not always 1 foot, but there's a certain time when the radius is 1 foot. And that's when we want to find this rate of this volume. So at this point, we need a diagram. We kind of have a diagram here on this side if you look at these, right? Dreads. We have our rates in a box and all our information. We have an equation because I gave it to you. Sometimes I don't give it to you, but in this case you have that blue equation here. And now we need to actually take the derivative of that equation. So here is where your calculus is going to start to come in handy. So let's look at this. I personally would recommend making this first. Actually, that's a constant, isn't it? So we can just leave that, we can just bring that down. 4 pi over 3. That's just done. Okay? What is the derivative of v? Well, the derivative of y is dy dx, right? If we're doing it for x. The derivative, we're going to do the derivative with respect to time, so it's going to be dv over dt. None of the variables are going to be in good shape and are going to be matching here because we're doing things with respect to time. So remember, we are going to differentiate with respect to time. So here we got that constant, leave it alone. Here we have to derive. So that's going to be 3r squared dr over dt. Okay, these are important skills from implicit, and if you're not understanding the differentiating with time, you've got to make sure you get there, okay? So this is canceling out, that's not necessarily. And now what we can do really is we've differentiated. Really what you do is substitute and solve now. But you do not substitute that r equals 1 in here. You do not substitute that r equals 1 into this top part, okay? This is very important because this is the most common mistake, is to take that 1 and plug it. I'm telling you what not to do. Do not put that 1 in there. Most common mistake on a related rates problem. So you don't want to do that. You want to follow this procedure. So the reason is because that r is going to be changing in this equation. So this whole equation is very dynamic. Okay, we have dv dt from up above. Hopefully you have it on your paper, 4.5. And we have the r is equal to 1. So I'm going to put in the 4.5, I'm going to put in the r is equal to 1, and I'm going to leave everything else alone. I guess I have 4 pi here times that, and that's really all I have. And literally, what am I looking for? I'm looking for dr dt. So the good thing is, it's really not that bad. You just divide by 4 pi, right, on both sides. And at that point, you found dr dt. And that's what we were looking for. This is the rate at which the radius is changing, 4.5 over 4 pi. Okay? That should be it. I'm just going to check. Make sure we didn't mess anything up here. over 4 pi. That's correct. And that will come out to a decimal. We'll round that to 3 decimals if we ever were to divide that out. So that's how the radius is changing. It is increasing as time goes on. So you will try this one. What I want you to know is that this is in the new Larson Calculus book, the blue one, with the QR code book, basically. And you try 13 and 15, but you can wait on 15 until later. So do fill 13 into here. To try 15 in this box at some point, but you don't have to do it right now. You can pause and try 13, and then you can come back for the 15, okay? So go ahead and pause the video and try 13 at least, and try 15 at some point. Okay, so hopefully you paused the video, you tried number 13, and hopefully you looked up in the back and you got it right. That's what we're hoping. And it was really a sphere question, so I'm hoping is very similar to the one we did. As I'm looking at the problem, it seems like it's pretty similar. It looks like the only difference was the radius was the rate they gave us, right? Now we're going to talk about the speed of an airplane. And you, by the way, you can go to this website to get a more clear definition of this, or a clear example here. But we have an airplane flying on a path that'll take it directly over a radar tracking station, as shown in this figure. I'll show you the figure in a second. Distance is decreasing at a rate. I'm going to underline that in red. That's decreasing at a rate of 400 miles per hour. When s is equal to 10 miles, what is the speed of the plane? That's what we're wondering, right? So I guess I'm going to start to kind of fill this in a little bit. But what I might want to do first is take a look at the diagram. So here we have it. All right, so I guess I have the following things. I'm looking for the distance. The distance is decreasing. So the airplane flying on a flight path taking it directly over a tracking station. The distance is decreasing at a rate of 400 miles per hour. So that can't be the speed of the plane. That can't be for x, right? It says, because they're actually looking for that. I guess in the end, we're looking for dx over dt is equal to question mark. That's the speed of the plane, right? We're looking for when s is equal to, that's s, sorry, is equal to 10. That's also in green there. And here's the deal. The distance, I think that's the distance between the satellite and the plane. So that's this distance. So I guess that's decreasing at a rate of 400 miles per hour. This is big because that's ds dt. That's the rate of that distance changing. That's the rate of that variable changing. And that's decreasing. That's a negative 400. The derivative would be negative. If you think about a function increasing and then a function decreasing, right? This is the positive slope. Positive derivative. When a function's decreasing, it has a negative slope. It has a negative derivative. We're just looking at a function that increased and then decreased. It had a negative slope or it had a positive slope, right? That's important. A negative derivative or a positive derivative. So we have a negative rate here. Because it's shrinking. It makes sense. Okay, we have a lot of things here. We have a triangle. Do you know any way that we could relate these rates? Is there something, dr, oops, dreads, dr, e, ds. So the diagram we have, the rates we have, it looks like. The equation, like an equation that'll relate these variables. Well, it's a triangle, guys. I mean, it's got to be x squared plus 6 squared is equal to s squared, right? And they're showing that that's 6 miles. The plane is not dropping. in height, right? It's going to keep the same altitude. So keep in mind that this is fixed. That's never going to change. So if you were going to take the derivative of that, it would be 0. The derivative of 6 is 0, right? The derivative, the change in that is not happening. It's not changing. So now we have our equations and we need to take our derivative. So with respect to time, it's 2x dx over dt, right? Plus 0, that's not changing at all. That derivative is 0 as well. And then 2s ds dt. And I think we had enough information really from here. We can basically just plug in. So let's look at what we got. Well, we have ds over dt is negative 400. So I'm going to go ahead and plug in negative 400 there. So let's make sure we understand that. That's right here, right? Negative 400 is ds dt, and we're just going to plug it in there. And then s is equal to 10, so we'll take the 10, let me change the colors, get it as clear as possible, because you'll probably be watching these videos for decades. The 10 is the s, so that's going to go here, right? And the dx dt is what we don't know. So that's 10 and negative 400. So we got 2x dx dt equals 20, I guess, right? And then it's negative 400. So that's where I'm at right now. Okay, so my issue is really this. I can divide by 2 on both sides. Pretty simple. That makes that 10. So I have x dx dt, right, is equal to, I guess that's 10 times 400. I guess that's negative 4,000. And that's where I'm at right now. But I'm not really solved for dx dt. So I'm going to go back to my diagram. I'm going to try to think about this for a second. Is there a way I can figure out x? Well, this is big. When s is equal to 10, right, I have this triangle basically. I have 6 here, I have 10 here. Agree? And I have x here, and I don't know what it is. We don't know what that is. Well, how can we figure it out? Just Pythagorean theorem, right? And by the way, it's a 3, 4, 5 triangle doubled. It's a 6, 8, 10 triangle. So x is actually 8 for that reason. Do Pythagorean theorem out if you don't believe me. Just do the whole Pythagorean theorem out. Negative 4,000 divided by 8, and that should give us our answer, okay? Geez, I think that's going to be 500. So negative 500 miles per hour, okay? We ignored units. We will talk more about units in the future, but for now, I think that's okay. Negative 500 miles per hour. The distance s is shrinking between those two objects at this point. So what you're going to try now for yourselves is page 194, number 21. It's talking about a ladder on a wall, and it's a big problem. These problems are very important as you go through related rates. So just know this problem is a big deal. So try that, and then that is it for the video and the guided notes. All right, we'll see you soon.